So the problem is this: electronic engineers have to often look through detailed data sheets because search engines such as DigiKey are not good enough. So for example, in this simple category of RF and wireless, we have over 85,000 items, and this is just one subcategory. So looking at the datasheet here, we see this RF transceiver. It has 78 pages, and this is pretty typical for electronic components. And if the search engine is not good enough, then we'd have to look through these datasheets all the time. Let's begin by seeing some results. Here we have an extracted datasheet. It's a set of features belonging to this manufacturer number. So looking at the datasheet, we see that it is an RF detector of 600 MHz to 7 GHz. Is that right? It is 600 to 7000 MHz. What about something more random like the power range, 2.7 volts to 5.5? Yes, the supply voltage range is also correct. So we see here that the model has been able to extract some useful features. We're going to solve this problem using a large language model. It's clear that we can extract features from the PDFs, the datasheets, using a language model. But how do we know what features we need to extract? Here we'll use Gemini's long context by inputting a dozen or so of the PDFs, a random sample of datasheets, and we'll ask it using a special prompt to extract features that is detected from all these datasheets. Then we'll create a structured output, a schema, JSON schema, that we can use for future iterations where the model will go through each datasheet and based on the schema extract the relevant features. And once we have these structured outputs, these JSON features, we can use it how we want to. We can use RAG, we can just put all of it in a context, or put into a database. We're going to use the Pro model to generate features. It is slow and more expensive, but we only are running it only once, and we want this to be really accurate. Getting started with the Gemini API is pretty easy. I recommend using the Google AI Studio to start and to tinker with it. You initiate your model. As such, you need a model name, a generation config, and a system prompt if you want to. The generation config can be also generated through the Google AI Studio for you, and if you want to tinker, I recommend doing it that way. I noticed on the source code that the temperature says is from 0 to 1. However, I think that is wrong, and it is from 0 to 2 as per the Google AI Studio and the documentation on the website. Select 20 data sheets that we're going to upload to Gemini for us to use as context. So we can easily upload a file through the GenAI upload file function. We can see that the total token size is 423,000-ish. You can now run your inference using the generate content function. The output of this looks like this. It's a comprehensive set of features that is detected from the 20 data sheets. This time we're using Flash, we find it to be good enough, and we're also doing structured output using JSON features. And now we have a schema. We're going to use that schema to extract the same features from all the other data sheets. We're going to run this probably hundreds of thousands of times for each of the data sheets, each of the components. So we need to cache that context so it's cheaper for us in the long run. Something to be aware of is that the cache content has a limited time span, and you insert that using a TTL parameter here. We find that the Flash model is more than good enough in extracting the features and creating a JSON file that's well structured. We showed the results at the beginning, so we won't go over it again. The long context model allows us to sample many documents in order to generate a standard set of features, which wouldn't be possible without a long context window. This then is used to create a structured schema, which in turn is used again to extract same features from hundreds and thousands of other data sheets.